Waves interact with convection by sort of in this region where there's uplift, where the air comes in and then goes up, conditions become more conducive to convection. So you get more convection here, and that pumps heat into the waves, and it moves moisture around, and in a variety of ways that can provide energy to the wave system. Either provide or take energy from the wave system. Right, so these waves are not well represented in the very complex global climate models that we use these days. You can look at the spectrum they produce, and it doesn't tend to look like reality. Right, which we think means there's something missing in their treatment of convection. So what we're trying to do is find a very simple system where we know exactly what's going on that reproduces these waves, so that we can nail down what is critical to the waves. Right, so what we have is a system of equations that represent the first two shallow water wave modes, so those two modes I showed, and they're coupled together by convective heating. Right, and convection is such a sort of, the novel part about convective parameterization is that the moisture of the mid-troposphere region controls how high convection reaches. If you have a convective cloud rising in dry air, it'll entrain that air into the cloud through turbulence on its edges, and that'll cause evaporation of the water droplets in the cloud, which will cool the cloud, make it less buoyant, so it won't go as high. If the same cloud rose in moister air, there'd be less of this drying, so it'll reach higher. So that's a fundamental part of this. So what that really means is that the more moisture you have, for a given amount of lower tropospheric convection, you get more upper tropospheric convection. And if we take this model and we look at, if we imagine we started it off just from nothing and we gave it a random kick, waves would start in it and they grow. So what we've plotted here are the frequencies and wave numbers of all the waves that we see growing in our model. And then the size of these dots tells us how fast they grow. So what we see here is very fast growing waves here in this region, which corresponds to the Kelvin waves, which were some of the strongest waves in the plot I showed. And we see similar microscopy gravity, and these are the inertia gravity waves. But obviously missing here is the Madden-Julian oscillation. That's the strongest feature on the spectrum, so we'd love to explain that with this model, but we can't yet. It's not terribly surprising, the Madden-Julian oscillation is not a shallow water wave. So there's no real expectation, but there was a hope. Right. So in summary, we have a model that produces a linear spectrum, that's what the growth rate was, that compares favourably with the observations. So what that tells us, we think this is about the simplest possible model, the simplest model that we can conceive of, that comes close to producing reality. Which I think is a strong hint that this moisture entrainment effect is very important and needs to be considered in more complicated models.
Yes, comments, questions?
So I just want to make sure I understood what fundamentally your model was. So it was the idea that you could treat the atmosphere something like shallow water waves, and what you expect in shallow water waves you are seeing.
Yes, what the link here is, yes, the atmosphere looks like, at least perturbations on the atmosphere, the waves going around, act like they're shallow water waves in many ways. And so we took the shallow water wave model and we got something that looks like reality. So we're confident that it has really, we're confident that we've done it right and it has important physics in it.
You said the
Madden-Julian oscillation?
What is the theory about what they are if they're not shallow water waves?
It's very much disputed. I've heard it said that there is slightly more theories than there are theorists for the Madden-Julian oscillation. It's really not well understood. It is improving. It's coming together. We have ideas, but nothing that I can show, or that I'm game to show.
So how does this idea of entrainment of moisture get incorporated into the shallow water wave model, or are they separate?
No, so what the model is, we've got equations for the height of the waves and the currents, which correspond to which correspond to temperature and wind. And then temperature is forced by heating. So the mid-tropospheric moisture affects the heating, which then becomes the temperature, and forces the temperature, which is the same as forcing height in a shallow water model, or injecting mass into a shallow water model.
Shallow water models have been around for a long time. So can you remind me again what it is that you're doing that's new?
What I've done that's new is summed up in this figure, really. The writing down functions of the heating, of the forcing. The most specific function of the forcing is novel, and that's what we've done that's different to other people who've done similar things. And we've got, I think, a better result.
So my follow-on was, how does yours compare to other shallow water models, and how is it measured? I mean, what in terms of how good it is?
There isn't a good measurement because these models are all very preliminary still. For one thing, what I've shown here are linear growth rates. What we see in this figure are sort of equilibrium powers. So I'm comparing apples and oranges, but the oranges might turn into apples if you assume constant damping. They're going to have to get technical. If you assume there's some sort of relatively constant damping acting on all waves that we're not including, it's non-linear, then the steady state amplitude should be proportional to the growth rates, the linear growth rates. So we're making that assumption to link this figure to my results, and the fact that they're close is good. But there are other things. There are observations that these waves are also stochastically forced by Rossby waves coming out of the extratropics. So these are additions to the model that I want to put in, but they require more complicated integration.